that's what x can be. For most functions, that's a lot of things. In fact, infinitely many things. So a better question would be to ask yourself, what can x not be? And there are 2 problems in Algebra 2 until you get to logarithms, and then there are 3 problems. 3 things that could come up in functions that cause domain problems. Square roots, because square roots can't be negative underneath. So if you're solving a domain question, you have a square root, you make sure the inside of the square root's not negative. Logarithms can't be negative or 0, so the inside of a logarithm has to be greater than 0. And the third thing is denominators, and what can denominators not be? So if I'm looking for the domain of a rational function, I'm going to ask, when is the denominator 0? My domain's everything else, right? So that's domain. Range, we're going to need a graph. Rational functions are too complex to work range without a graph. That does not mean we need a calculator. A lot of people think when I say we need a graph, that means we need a calculator. Some of them we will need one. Some we can do without a calculator. It depends on the difficulty level. Vertical asymptotes come from domain issues. At vertical asymptotes, we have an undefined place on the x-axis. However, there are 2 things that could happen. As you may remember, there are 2 possibilities. There are asymptotes and there are holes. You need to know the difference between your asymptotes and your holes in the text, right? So, asymptotes happen when the factor that causes the domain issue does not cancel. You can't cancel it. It's called a non-removable discontinuity. It affects the graph at more than just that one spot. A hole only affects the graph at that one spot, and that's because otherwise, anywhere else, you could just divide it out. Like we had x minus 3 over x minus 3. For all practical purposes, everywhere except at 3, that's just the value 1. So holes are called removable discontinuities. They're the excluded domain values that remove. X-intercepts and y-intercepts, I have them under rational functions, but this is really any function. To find y-intercepts, you put 0 in for x. To find x-intercepts, you put 0 in for y. Now, we do have to be careful with holes because holes can't both be a hole and an intercept. An intercept is a place I cross the x-axis, so obviously at holes that does not happen. Horizontal asymptotes are the ones with the rules. Y'all remember the rules? You had to follow the rules on those. If the numerator and denominator have the same degree, then your horizontal asymptote is the ratio of the leading coefficients. If the numerator has a higher degree, then there's no horizontal asymptote. And if the denominator has a higher degree, the horizontal asymptote is y equals 0. I'm going to walk you through why as we work a problem. Why that works the way it does. It might help you remember those rules slightly better. Oblique asymptotes or slant asymptotes happen when the numerator is exactly 1 more than the degree of the denominator, and you find that by dividing out the polynomial using polynomial long division, or in special cases, synthetic division. And that's how you find the slant asymptote. So, I have a couple examples here we're going to walk through. We're going to graph as much as we can in the next 20 minutes. And I put these side by side for a reason, because I like the comparison of the 2. To answer domain, what's the first thing I need to do? Find when the bottom equals 0, and by factoring, I can do that much easier. And you'll notice these actually have the same denominator. These 2 functions have the same denominator. So, what is the domain on both of them? 3 and negative 2 are what x can't be, right? Everyone agree with that? Because that makes the bottom 0. So, what's the domain?
Negative infinity to
Everything else. Good, and there's 2 ways to write it. There's interval notation, negative infinity to negative 2, -2 to negative, or -2 to +3.
So 3, -2 are the wholes.
Maybe.
Do you get to write the U between each one?
I'll take it either way. And the other way to write that is set notation. For this particular problem, I prefer set notation. Miss Lowe probably made you do interval notation to practice. At this point, you're grown-ups now. You can make your own decisions on whether you want to do set notation or, whoops.
What are those little U's?
They're a union of two sets. If you left them out, no one would count it off. They're just good mathematical notation, but they said this and this make up the domain. They use a mathematical notation for a combination of two sets. Have y'all seen set notation, right? No. So what it says, set notations, a lot of times you use it to list things. That's like if you're just listing numbers. But this says x such that x doesn't equal -2 and 3. So either way works. They're both great. Interval, set, two different notations to say the domain. Some people get a little more technical with this notation, and they say x is a real number such that x doesn't equal -2 and 3. So you may see that in the textbook. So got options. I'm going to do the range. When am I going to do the range? At the end, after I have the graph. I guess I'll rewrite it. I was about to put it up. Okay. So negative infinity, -2, -2 to 3, 3 to infinity. Okay. So that's, why are these two domains the same? Same denominator, right? The denominator is the only thing that matters for domain. Vertical asymptotes. Where do we find those?
On the y-axis.
The -2 and the 3 are our candidates for vertical asymptotes, right? What do I have to be careful about? Holes. This one has a hole.
Yeah.
The other one doesn't. So on the left-hand function, both domain issues are vertical asymptotes. I will be picky on this. Vertical asymptotes are equations of lines. So if you just write -2 or you just write 3, I will count off, because a vertical asymptote is an equation of a line. So it needs to have x equals. What I'm really looking for is that you know it's x equals and not y equals, so that you know which one we're talking about there. On the right-hand one, the only vertical asymptote is x equals -2.
Oh,
That means on the left-hand function, I have no holes. On the right-hand function, I do have a hole. Where is it at? At 3. And I actually, and this may be an extension from Algebra 2, I'm not sure. I want you to tell me the x and the y value of the hole.
Let's plug it in.
Good. Plug it in where?
Into the equation.
Into the equation after the hole has been canceled. Because what we're wanting to find is where would it be if it could be there? We know it's not. We know it's a hole. But where would it be if the x minus 3's weren't there? And so would you agree this function reduces to 1 over x plus 2?
Mm-hmm.
So 1/5. So this function reduces to 1 over x plus 2.
3 plus 2.
So at 3, I would be at 1/5. Now remember, I'm not there. It's undefined. But there's a hole there at 1/5. You don't know it, but when Miss Lowe made you do that, you were doing some calculus. We'll talk about that later. Next chapter. There's a reason she makes you do that.
So vertical asymptotes are in the denominator.
Right, and the ones that don't cancel.
And the ones that don't cancel.
What if, like, like that it cancels on the bottom, like there's one on the bottom, there's two on the top. Wait, how do you do that?
Then it is a whole.
I know, but like you put it into the thing and it has a zero. So it's
On top though, right? There's two on the bottom or two on the top. If there's two on the bottom, then it's a vertical asymptote. So then you plug it in, you get 0 on top, right? Because the bottom canceled. Bottom's gone.
It's like,
yeah, you get 0 on top. You do get 0 on top. 0 over 1. Because the bottom canceled, right? Okay, so you get 0. So the y value is 0. You see what I mean by that?
mm-hmm.
Yeah. X-intercept. I want the function to equal 0, correct?
Set it equal to 0.
So set it equal to 0. When do fractions equal 0?
And the top is 0.
When the top is 0. So the first one at 1, everyone agree? The second one, you might be tempted to answer 3.
No, it crosses out. It's a whole.
Good. It can't cross the x-axis there and have a hole there. That doesn't make sense, right? So there is none. Y-intercept, what do you do? Put 0 in for x. So I get 0 minus 1 over 0 minus 6, or 1/6. I don't care how you write these. I am putting them in point notation. If you said x equals or y equals, I would not count off for that.
For the other one, do you have to cross out the holes or?
It doesn't matter.
Okay.
Either way. It's probably safe to cross. I don't know. You'll get a half either way.
There'll probably be some.
Yeah, the only time you would have to be careful about it is if the hole is on the y-intercept. But hopefully you've figured that out already up here if that happens.
Will we get any of those for homework?
Maybe. Anything's fair game. Okay, horizontal asymptotes. Horizontal asymptotes are the rules, but I want to walk you through why the rules are what they are. Horizontal asymptotes are what's happening, and I would pay attention to this. I know you got your homework and you know how to do it, and so, but I would pay attention to this because I don't know if you know why or not. Horizontal asymptotes are what's happening as x gets really big. Isn't that what x levels off, what the function levels off to be as x gets really, really big? We agree with that? As x gets really, really big, you might have remembered with polynomials, the leading terms take over. So these two would be the leading terms. They take over as x gets really, really big.
Can I speak for a minute?
Okay, as x gets really, really big, what happens to x over x squared? Which would reduce to 1 over x. Would we agree with that? Think about really big numbers. If I divide by really big numbers, what do I get?
Really small.
Little bitty tiny numbers. Towards 0. We agree with that? So the horizontal asymptote is y equals 0. Now we could obviously follow a rule for that, but do you see why that rule works? As x gets really big, that leading power is going to take over. We're going to end up dividing by really big numbers, which is going to make our function go really small. So if the denominator is bigger, your horizontal asymptote is y equals 0. That's the rule. That's why the rule is what it is.
Can you go over the rules about the x's? The x on top is bigger.
I will once we get to an example. We may not get to one today, but when we do, I will. We will get to one eventually. And so this one would also be y equals 0. Everyone agree? Okay, graphing. I'm going to put all that information on paper. I have a horizontal asymptote at y equals 0, so I'm going to draw a dotted horizontal line. If it truly is at y equals 0, you're probably not going to be able to see it because it's at y equals 0, but you can see mine because I have red. The y-intercept is 0, 1/6. The x-intercept was 1, 0. there were no holes. Vertical asymptotes at -2 and 3.
That's confusing.
What is?
Is there an asymptote?
A horizontal
Oh,
asymptote?
is it the whole? Never mind. No, it's fine.
A horizontal asymptote can be crossed. Good question. Very big misconception. A lot of people think you can't cross asymptotes. You can't cross vertical asymptotes because they're undefined places. Horizontal asymptotes can be crossed all day long if we need to. An asymptote, by definition, is a line that a graph approaches, not a line that is undefined. Vertical asymptotes are undefined because of where they come from. But horizontal asymptotes are just what happens as x gets really big. So in the center, who knows what's happening in the center? Good question. There is no hole. Okay, looks like that, right? To finish off this graph, would you agree that I know this only crosses the x-axis at that one place? If it crossed anywhere else, I would have found it. And these lines are the lines the graph approaches. Think of them that way. So I know this goes up like that here. How do I know that? Because it can't go back down or it would cross the x-axis again. Now, it's not because of the horizontal asymptote that I know that. It's because of the x-intercepts. I found all of the x-intercepts. So there aren't any extras. What I don't know is if this bounces back up or if it crosses the x-axis. I do know. If you know multiplicity, you might know that even. We'll talk about multiplicity another day. But what I would do to find out if it goes up or down is I would plug in 1 into the function. Right? Go plug in 1. If you get a positive number, it's going to bounce up. If you get a negative number, it's crossing that vertical asymptote going down.
How is it? Oh, it's like 2 separate. Is the dot on the line?
On the horizontal, yes. So you missed that conversation.
Yeah.
You can cross a vertical or a horizontal asymptote. Horizontal asymptotes are just lines that the graph approaches as x gets big. They can be crossed. They will be crossed at your x-intercepts.
How do you decide?
Plot. Well, this one I had no choice because I can't cross the x-axis. This one I picked plug in 1 and find out if it goes down or if it goes up. Am I done?
Yes.
The domain was negative infinity to -2, 3 to infinity, so I don't think so. I need this part of the graph and this part of the graph. If you've done enough graphing with rational functions, you probably have a good idea of what these look like. The only thing you don't know is whether it's up here or down there. How could you find out?
Plug in a number.
Plug in a number. Pick one. For speed, if you want to use a calculator, that's fine. I hope you could plug them in and find out if you get positive or negatives if you had to. So anyway, plug in 4 and -3. It's positive on the right. Well, don't guess. 4 minus 1 is positive. 4 minus 3 is 1. 4 plus 2 is 6. So 3/6, which is a half. So that's positive. So at 4, I get positive 1/2. So that means this side looks like this. Again, -3. Again, -4 on top. -6. It is negative. So I get this graph here. Sort of. It could definitely be better. That's a really good picture with minimal work. Because of the middle piece, what's the range? Negative infinity to positive infinity. As soon as I saw that middle piece, wouldn't you agree the range goes all the way from the bottom to the top? Okay, tomorrow we will do more examples. We will spend all day tomorrow just doing examples on rational functions and polynomials. Polynomials probably will only need one example to be good. Rational, we need a few. Any questions before you go? We still have a minute or so. Any questions on the ones I just finished? Sit down and let people ask if they have them. Any questions on this one? Any questions? Now the one on the right looks different. We still need to work on it. I'll probably have you finish the graph of it as a paper here tomorrow. Did we learn some things that we've forgotten? Rational functions? Do what? Remember? No, both do Thursday.